Lesson 4 of Chapter 2, Part 1 is on zeros of polynomial functions. First thing we're going to talk about is a rule that we have that polynomial functions of degree n have at most n real zeros. So if you look at the display you see right here, we have a second degree polynomial function. Here it is in a factored form right there. And thus we can see that both zeros are real zeros, -3 and 2/3. Both of those are real and both of those are rational. What does it mean to be rational? It means it can be written in the form of a fraction. Now here's another quadratic equation, which means it has at most 2 real zeros. We can put it in a factored form, and you can see that factored form here. And so it does have 2 real zeros, but both of these real zeros, as you can see, are irrational. What does it mean to be irrational? It means that they can't be put in the form of a fraction. A lot of times irrational values are square roots. A lot of times it's non-terminating, non-repeating decimals. Now we have a theorem called the rational root theorem. It looks really complex. It says if you have a polynomial function written in descending order, then every rational zero has the form p over q, where p is factors of your constant at the end, and q is factors of your leading coefficient at the beginning. So a couple of examples to help you understand this rational root theorem. It says list all possible rational zeros of each function, then determine which, if any, are actually zeros. So what we have to do is come up with p and q. Well, p is factors of your constant, so plus or minus 1, 3, and 9. Those are the numbers that go into that. And then q is factors of your leading coefficient, which, even though there's no number in front of that x to the fourth, it's a 1. So it's plus or minus 1. So possible rational roots are p over q plus or minus 1, 3, 9 divided by 1. So that just gives us 6 possibilities, plus or minus 1, plus or minus 3, plus or minus 9. Now, after we determine the possible rational zeros, those 6, as I've got in the box, it says then determine which, if any, are actually zeros. Well, if you look at this graph, it looks like it crosses the x-axis at about 1.6, 1.7, someplace there. Looks like it crosses at -1. I don't know, -1.8 maybe, and then also at -3. So we have 4 x-intercepts. So which, if any, are zeros? We have -1, and we have -3. So it must be that this is a rational zero, this is a rational zero, and these must be irrational zeros. Because I don't see it cross at +3, I don't see it cross at +1, and it doesn't cross at 9 or -9. Another problem done the same way. List all possible rational zeros. So x equals p over q. P is factors of your constant, plus or minus 1 and 2. Q is factors of your leading coefficient. So possible rational zeros are any combination of 1 and 2 divided by 1. So it looks like we have 4 possible rational zeros. And then list if any of these are actually zeros. So we graph it. Looks like it crosses at +1. Looks like it crosses at about -1/2. And looks like it crosses at 1, 2, 3, 4, 5, about -5.5 or -5.6. So with that being said, it looks like we've got a rational zero here. This must be irrational, and this must be irrational. So it looks like 1 is the only rational zero we have. Now here's one more problem done the same way, same directions. List all the possible rational zeros. I'm going to give you 3 problems like this in your homework. And if you take a look, some of them are a little bit more complex than the last 2 that we just did. If you look at the p over q, P is factors of the constant 8. Q is factors of your leading coefficient 3. So I've got those listed there, plus or minus 1, 2, 4, and 8, divided by plus or minus 1 and 3. So now your list ends up looking like this. It's a pretty long list. It's any combination of the blue numbers over any combination of the red numbers. So 1 over 1, 2 over 1, 4 over 1, 8 over 1. But then you have to also consider 1 over 3, 2 over 3, 4 over 3, 8 over 3. Okay? Then determine which, if any of these, are actually zeros. So we graph it. It looks like it crosses at -2, and that's listed right here. Looks like it crosses at 4, and that's right here. And then it looks like it crosses at about, I'd say that's about 1/3. So it looks like all of these zeros are rational zeros. -2, 1/3, and 4. So that's the rational zero theorem or rational root theorem. Last thing we're going to do on this first part of lesson 4 is you're going to be given an equation or a graph, and you're going to be asked to solve the equation. Now to solve it, you just have to give me the x-intercepts. Okay? If I were to write an equation for this graph, it would have to be, let's see, 1, 2, 3. There's 4 turning points. It's a discal guy, Randy, so I'm going to guess it's going to be a 5th degree polynomial. So this would be the equation that I would come up with. Looks like it's touching at -4, so I'm going to say x plus 4 to the 2nd power, multiplicity 2. Looks like it touches at 0, so I'm going to put an x squared in it. And then it looks like it crosses at 3, so I write x minus 3. So my solutions, my zeros, are 3, 0 of multiplicity 2, and then at -4 with multiplicity 2. So you're listing the zeros and any multiplicities. Here's another one. It's just going to say solve the equation. So you just take the equation, you graph it on your calculator, and you look for the x-intercepts. I've got the graph listed here. It looks like it crosses at +1. Looks like it crosses at +2, and looks like it touches at 3. So the equation that I would come up with would look like this. X minus 1, x minus 2, and then x minus 3 with a square on it, multiplicity 2. So my zeros, my solutions would be 1, 2, and 3, and the answer at 3 is multiplicity 2. Okay? So that is part 1 of lesson 4, chapter 2. Homework problems you're going to be working on tomorrow are page 127, 2 through 4, 10 through 16, collected on Tuesday.